Okay, hi everyone. Today we're going to go ahead and talk about something called molecular polarity, which is telling us whether or not the molecule is polar or nonpolar. We're going to talk about what those terms mean. So first, I'm going to go through a few definitions. Just a reminder, electronegativity is the tendency of an atom to attract a shared pair of electrons towards itself. So only atoms that bond are able to be described using electronegativity. So the noble gases that really don't bond with anything, they do not have electronegativity values. Otherwise, electronegativity increases as you go across a period left to right and as you go up a group. So in this case, fluorine is the most electronegative element on the periodic table. And the further we get from fluorine, the less electronegative we are. Okay, so two other terms, nonpolar covalent bonds. So we're going to talk about this quite a bit today. So this is a bond where electrons are shared equally between two atoms. And then polar covalent is the exact opposite, a bond where electrons are shared unequally between two atoms. So they're still sharing, they're just not being nice about it. Okay, and then we have the term dipole. Dipoles are a separation of charge between two covalently bonded atoms. And we have a dipole whenever we have a difference in electronegativity values, which causes one atom to kind of pull the electrons closer towards itself, and the other one has fewer electrons around itself because they're getting pulled towards the other one. So we end up with kind of a positive part and then a negative part. And we can denote dipoles using two different systems. So the first one uses the Greek letter delta, that kind of curly Q symbol there, with either a positive or a negative sign after it. And we pronounce this delta positive or delta negative, where delta positive is by the less electronegative element, and the delta negative is by the more electronegative element. We can also use an arrow, where the one end we have the point and the other we have the line drawn through it. And if you kind of cover up that the right-hand part where the point of the arrow is, and just leave the left-hand part of the arrow showing, we see a plus sign, okay? So that plus sign goes over the less electronegative element, so the partial positive, and the point of the arrow is going to go towards the more electronegative element, so it shows where the electrons are being pulled towards. Okay, so just to kind of show this one another way, again, the dipole arrows, the less electronegative element has that positive over it because it's partial positive, and the more electronegative element has the point of the arrow. For the delta symbols, we have the delta positive over the less electronegative element, and we have the delta negative over the more electronegative element. Okay, so we work through two examples. The first one, we have chlorine, Cl2, bonded with itself. Well, if we think about this, two chlorine atoms, they're exactly the same, so they have the same electronegativity values. Therefore, they are sharing their electrons equally. There is no unequal sharing. It's like if you shared exactly with your twin, okay? Equal sharing, so no dipole. So we don't have those delta symbols. We don't have the arrow. However, hydrochloric acid, HCl, in this case, chlorine is more electronegative than the hydrogen. So it's going to pull the electrons towards it. So we have that kind of positive end over the hydrogen and the point going towards the chlorine. I could also have it where I have the delta positive by the hydrogen and the delta negative by the chlorine. Either way is acceptable. Okay, so when we think about these electronegativity differences, they can actually help us determine the type of bond that we have present in our compound. So a difference of 0 to 0.5, so less than 0.5, gives us a nonpolar covalent bond, meaning that we're sharing those electrons pretty equally. We don't have really any dipoles found. Between a difference of 0.5 and 1.5, those are polar covalent compounds. And anything with a difference of more than 0.5 is going to be ionic. Now, I just want to point out these are kind of rule of thumb values. There's different values depending on who you talk to, but this is kind of the average of what you usually will see. So if you look online, you might see slightly different values. That's okay. But this should be a good guideline whether something's polar, nonpolar, or ionic. Okay, and we get the values from a table of electronegativity values. So these are actually in your notes, so make sure you look for them. But all those little blue values there, those are the electronegativity values for each of the different elements that have known electronegativity values. Okay, so we're going to work through some of these examples and answering the question, is the bond polar for these compounds? Now keep in mind when we think about bonds, it's between two different atoms. So we're going to think about the two atoms that are involved for each of these types of bonds. So for NH3, it involves one nitrogen and one hydrogen. So if we go ahead and figure out the values, nitrogen is 3.0, hydrogen is 2.2. That's a difference of 0.8, which is polar covalent. Okay, because it's between 0.5 and 1.5. For sodium chloride, now notice I actually kind of switched it first and took the bigger number minus the smaller number, so chlorine minus sodium. That's okay, because we're going to have positive values. We cannot have negative differences. So in this case, sodium chloride has an electronegativity difference of 2.2, which makes it an ionic bond, which we know because we have a metal and a nonmetal. Next one, I2. We have two iodines binding together. So the difference for this one is 0. So this is non-polar covalent. And then finally for methane, we have CH4. We have a carbon bonding with a hydrogen. So 2.5 minus 2.2, which gives us a difference of 0.3. So non-polar covalent overall, although it is more polar than the I2. Now the one thing I want to point out, kind of taking the difference of the I2 is a little silly because I already knew the answer of this one, that all of the diatomic molecules, remember Hankel-Brick, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. All of those elements are diatomic, meaning when they're by themselves, they're going to bond with their twin. All of these diatomic molecules will have an electronegativity difference of 0 because we're subtracting the same element from itself. And because of this, they will have non-polar covalent bonds. Okay, so molecular polarity is thinking about polarity as a separation of charge. So there's two different cases here. We have bond polarity, which is what we just went over, and we have molecular polarity. Bond polarity is the simpler of the two cases. It only depends on a difference in electronegativity values. Molecular polarity, in contrast, has a difference in electronegativity values, and it has a molecular shape that is polar. So an analogy for molecular polarity, we need to have two things that are true. So in order to be a successful NFL quarterback, you need to be both big and fast. Because if you're not big, you're going to get crushed when you get tackled the first time. And if you're not fast, you'll never score any points for your team and you won't stay in the NFL. So you need to be both of those things. So to be polar, a molecule must have a bond that is polar, so an electronegativity difference of greater than 0.5, and have a shape that allows for a separation of. Okay, so you might be wondering, what does it mean to have a separation of the charge? Well, quite simply, the electrons are being pulled in one direction and are not being pulled back or canceled by a pull in the opposite direction. So you can actually demonstrate this yourself at home. So with one of your hands, go ahead and make a fist, and if you push in one direction, your fist moves. That's because there's nothing canceling it out. Well, you make two fists and you push against each other, assuming you're pushing with equal force with both hands, your fist don't move. The center stays the same. That's because we have that cancellation of charge. So there is no separation of charge. Versus where our dipoles don't cancel out, that's when we have that separation of charge, that movement. So I hope that helps. Bye. Okay, so another way to think about this is the shape polar, is asking yourselves, is the shape symmetrical? If the shape is completely symmetrical, then the shape is nonpolar. If the shape is not symmetrical with the atoms around it, then the shape is polar. Okay, so if we look at this, the shape, thinking about the Vesper theory with the molecular geometry, this is trigonal planar because they're all flat. Is it symmetrical? Yes, it is. Okay, so is this shape polar? No, because it's symmetrical. Okay, this next one, okay, we have For atoms with no unshared pair, so its steric number is 4, so it has a tetrahedral shape. This is symmetrical because if we draw lines through it, it's the same every single way. So is this shape polar? No. Okay, this one, same shape, we still have tetrahedral. But now we ask ourselves, is it symmetrical? In this case, the answer is no. Okay, because that yellow atom is different than the white ones. So it's not symmetrical in all directions. It's symmetrical in some, but not all of the directions. So because of this, the shape is polar. Now, if you look in your VSEPR theory chart, I have listed the shapes that are polar versus non-polar generally. So that's a good rule of thumb you can use. But otherwise, think about this idea of whether or not it's symmetrical. Okay, so let's work through one example of this, water. We want to figure out whether or not it is polar. Well, we need to first ask ourselves, is there a polar bond? So we're going to take the difference between the oxygen and the hydrogen. Now notice, even though I have 2 hydrogens, I just subtract one value of 2.2 because I'm just thinking about the bond of O and H. So in this case, I have a difference of 1.2, which is a polar bond. Now, think about a separation of charge. Okay, so that's my Lewis dot diagram. That is the bent shape. And if you look in your notes under that chart, you will see that it's usually a polar shape. But if we ask ourselves, is it symmetrical? Well, left, right it is. But if we compare up and down, it's not symmetrical because I have the 2 lone pairs up top. So this is the bent shape, which is polar. But because I have a polar bond and a polar shape, water is one of the key examples of a polar molecule. Okay, so I hope this helps. If you have any questions, please go ahead and let me know. Otherwise, have a great day, everyone. See you later.